Hey guys, good weather is upon us finally, so time to start looking at some e-bike projects. So this here is a women's e-bike's Meridian TeV-500, probably 8 years old. Got it on a good price from Craigslist. Lady said it was working fine, but just needed some batteries. And like all things on eBay, or sorry, Craigslist, of course when you take it home, you notice it doesn't work. So what does this thing do or not do? Well, there's a few problems with the bike, but mainly the issue is battery related. So when you start driving on the bike and you turn it on, as soon as you put some pressure on it, then it just shuts off. And usually that's an indication that the battery cells are weak, and as soon as you put some load on it, then the BMS cuts off. And of course you have to unplug the battery and plug it back in before it turns on again, because there's always a bit of a draw on that. So the goal here is to take the battery apart, test it, load test it first of all, and then fix the issue obviously, and get it back up and running. And all the other minor things like the lights and that type of thing, that's all going to be, that's just minor stuff. So let's get the battery out and take a closer look and see what the issue is. So the lady that I got this from, basically she said that this was a new purchase for her, and I believe it was lead acid, and then the lead acid was upgraded. So I think the case is the same, but somehow there was some sort of a service where this was updated, and I can see here 24 volt lithium, so I think you wouldn't write that unless you've done a modification. August 2012, so this is what, 8-year-old battery, so it doesn't work. So I got all this stuff from her, so let's give this a shot. We'll open it up, see what's going on, and see if we can fix it. So this is the charger for this. This is just your standard 3-hole charger. So if you turn this on, I see a red and green. Okay, so red means power on, yellow means charging, green means either full charge or disconnected. Alright, so let's see what happens when this thing gets a charge. Does the light change? Let's see. Light does not change. Okay, so that means that the most likely the BMS is disconnecting itself from the batteries. So which means that the batteries are doing something, the BMS doesn't like it, and it's shut this off completely. So this this light hasn't changed at all, which means that most likely the batteries have either gone to sleep or just are bad altogether. So let's take this apart. There are a lot of screws here. The lock assembly is here. There's some screws here. Okay. And let's just check for battery negative and battery positive. So this looks to me like it says B minus, and this looks like it says B plus. Oh, 23 volts. Okay. Looking at this BMS, I'm starting to notice some strange things. So I think I'm either not understanding what this BMS is doing, or perhaps I'm going to learn something new that I didn't know before today. But anyway, let's take a quick look at it. So upon first looking at this BMS, everything looks okay. But when you count this up, you get 1, 2, 3, 4, 5, 6, 7, 8 transistors. So 1 charge, 7 discharge, I guess. And then you count the resistors, 1, 2, 3, 4, 5, 6, 7. So there's 7 balance resistors. And then you count the wires. So this is your balance lead. Wasn't sure what this one was, but this is a balance lead. So if you count those up, there's 1, 2, 3, 4, 5, 6. And the counting according to the silk screen here starts at B1. So 6 times 4 is 24. And if we look at where's our battery charger? So very clearly, this is a lithium-ion battery charger at 24 volts. So 6 cells in series times 4, 24. Oh, that makes sense. Until you notice that there's actually 7 cells here, not 6. There's 7. So 7 times 4 is 28, not 24. So what's going on here? Why is it charging at 24? Okay, so I measure the leads of this guy here, and it looks like it's overcharging to 28. Sometimes the float charge is a little higher, but this is a 24 volt system. So how are you getting 28 volts on this? All right, so upon closer Googling, I found the circuit board on Alibaba. So woe and behold, there it is. This is their recommended design, which, as you can see, looks suspiciously a lot like our design. And as you can see here, if we take a look at this a little closer, as you can see here, we have all these resistors populated. So how does this thing work? Well, this is how it works. You see those little jumpers there? You see a 6, 7, 8 right in the middle of the screen right there, 6, 7, 8. So this is a multifunction BMS. It can hold up to 10 cells, from 6 to 10. So if you want 6 cells, you solder blob the 6. If you want 7, if you want 8, or you want 9, you solder blob them. Or if you want 10, you leave it blank. And so that's why there are 10 balance resistors. In our example, the top 3 are not populated. 1, 2, 3, 4, 5, 6, 7. So this is a 7-cell configuration. Okay, so got it. Now that's what that means. But also, interestingly enough, this is a lithium-ion slash lithium. Oh, actually, where's our thing here? Yeah, so it's a lithium-ion slash lithium iron phosphate. Okay, and as we all know, the lithium ions have higher overcharge than these lithium phosphates. In fact, these guys here have a very narrow range of operation, but can discharge pretty well, right? So the lithium phosphates, 3.9, their nominal voltage is 3.5, and their lowest discharge is 2.0. So what is actually happening is, I believe, this, and I've seen this before, and this is the reason why I'm saying this. This is very similar to another e-bike that I did a while ago, and it was a iron phosphate battery. These are iron phosphate cells. So this is an iron phosphate BMS. So if you look at ours, again, I theorize that this is actually an iron phosphate battery, even though this says lithium ion. So charging the lithium ion 6-cell 24 volt is like charging an iron phosphate 7-cell at the higher voltage. It's the same thing. Although you're over voltaging it, you're actually protecting it because the BMS protects over voltage. So you're actually injecting bad voltage into a, cross your fingers, hopefully working BMS, and you're ending up charging these iron phosphate batteries. So I don't know if that's how everyone does it, and I'm just learning something new, or not sure what. Anyways, back to the last thing I want to point out is, yes, so here we go. So normally on these bounce wires, you start at B0 and you go to BX. But in this case, what you're actually doing is on a 7-cell configuration, as you can see here, this is 7-cell, you're actually only wiring up 1, 2, 3, 4, 5, 6, and the 7th one goes to B plus, right? And because a BMS needs a plus and a minus, B plus, B minus, ours doesn't have a thick one like this one does, you see? See this big fat wire? Ours doesn't have that. So instead, what they've done is they've wired the last battery to this, because this one's not going to suck a lot of current from the plus. I think what they've done is, this is if you want to run a fat wire from here. They haven't done that. They ran the fat wire directly to the leads. So that's what it, anyway, this is my theory. Let's open this thing apart. First of all, let's measure it and see what's going on. And then we'll go from there. All right, so if we switch on the power supply here, I don't know if you can see that. See how it kind of goes from yellow to green. I don't know, maybe this is an old clunky one. But yes, we can plug in our power. And so if we measure battery plus and minus, so there's battery minus and battery plus. Do we see our, yeah, so 24 volts. So this will go a little higher, but essentially will hover around there. So this is stopping at 24. So on a 7-cell lithium ion, it's definitely not getting a full charge. So this has to be lithium phosphate, sorry, iron phosphate. It has to be. So if we take a look at the measurement, so this is B plus, B minus. So if we just look at the difference here, so you'll notice 3.9. This thing creeps up, but it doesn't go over 4. So this BMS is kicking in and protecting these cells. So this is cell 7, 6, 5, 4, 3, 2, and the last one, 1. So this is the problem. This last cell reads 0.9 volts. So that's the problem with this battery, that this cell is dead. Now it's close. It actually reads, you know, 0.9, yeah, 0.91 volt. Yeah, so this thing should be just shutting off completely. I'm not sure what's waiting for, but it does register voltages. You can see here, if we put P plus and B minus, right? Oh, sorry, plus and P minus, sorry. Right, it actually is registering. And I think what's happening is the beeping noise on the bike is actually this thing cutting in, cutting out. So it's detecting an off voltage, and that's where that beep is coming from, I think. But yeah, this cell number 1 is there. As you can see here, C7 is jumpered, right? So this is C7 configuration, and this is an iron phosphate configuration. I don't know where the jumper is for that, but it's probably under this blob here. So these things are just blindly made as a phosphate configuration with a 7S configuration. Anyways, interestingly enough, the first cell is dead on this one. Now, by total coincidence, the last one that I did also had the first cell dead. The rest of them were fine. So I wonder if that's how iron phosphate batteries die. Or that's just a coincidence that the first cell was bad. The rest of them are fine. I don't know. But that could be how it works. See, it's creeping up there a little bit. 1. I don't know if this ever creeps up to 2 volts. It may creep up to 2 volt. I don't know. Anyways. But yeah. So that's what's wrong with this pack here. I'm not even going to bother balancing this or load testing this thing because the first cell is dead. And who knows what this BMS will be doing. So let's open this up time and see what's going on. Okay, so I'm just curious to see how good the rest of these cells are. So the first bank we know is bad, but there's 6 other banks which seem to be charged up as a normal iron phosphate is. So I just hooked up from battery 1 output all the way to battery 7. So got on the test bench here. This thing is running at 5P, so 5 in parallel, 7 in series. So 5 parallel at 2.1 amps. This thing should be able to do 10 amps no problem for an hour. So we'll get this thing. So I just kind of I did a quick test here. So this guy here is running 11 amps. So we should be able to run this thing at 11 amps for an hour. Let's just see how good this is. So I'll kick off this test now, and oh, stopped. Start that again. Ooh, that's not good. Hold on. Let's try it again. Quick test. Start test. All right. Ooh. Oh, well, this is terrible. Oh, they're gonna die soon. Oh boy. Oh, there you go. Okay, this lasted 10 seconds. All right. Okay, these batteries are garbage. Okay, so before fixing the battery, I thought I would just maybe jump the battery with some good power and see what happens. And it seemed like this spike used to work, but doesn't work anymore. It just kind of beeps and beeps. Used to work, but no longer. So I jumped the motor directly. If you just kind of give power and ground to the motor, you can actually get this thing to turn, as you can see. Alright. So that's good. That means the motor's working. Okay, so upon closer looking at this wiring here, it really comes down to these two sensors. Now both of these come from this torque sensor. I'm not sure what the little one does, but it appears that the big one is actually the cause of the signal. So if you can take a look at the voltmeter here, you got black, you got white, red, and black. I believe white is just ground. Red seems to be 12 volts. Oh, I gotta shut it. I gotta turn it on first. So red, 12 volts. White, probably ground. And black is a sensor. So it says 1.1 volts. Right? And as soon as I start turning, this guy here starts to register, right? So I think that basically how this works is it applies a 12 volt signal to this, and the torque is a measurement between a resistance, which translates to a voltage between 1 to 12 volts. Okay, so this is the schematic of the proposed Arduino circuit. So essentially we have three voltages here. We have raw power, then we step that down to 12 volts, which is used basically just for the throttle, for the torque sensor, and then we step that down to 5 volts, which essentially powers Arduino and a bunch more related 5-volt stuff. So from the top left here, we're going to have a big power MOSFET, or maybe two, that will drive the motor in NPN configuration. So essentially motor gets power, raw power directly, and then the negative lead of the motor goes to the MOSFET, and then the gate driver of this MOSFET will be coming down here through a gate driver circuit or chip, and then be driven by the Arduino. We're going to have diodes from source to drain, and then also we're going to have external flywheel diodes for the motor, so to suppress as much voltage spikes as possible, because there will be a ton of current flowing through this thing. Then we're going to have a 12-volt regulator, which will take the brunt of the power regulation, including trying to handle spikes as best as possible. And then the output of that 12 volt will be going to the 5 volts. So that 5 volts should be as clean as possible. So that'll be driving the Arduino. It's also going to go to the throttle, and the throttle output will be going directly to the Arduino. All these blue things are essentially going to be driving the display, most likely through a transistor array, and then out to the display. And to the right here, raw power is going to be coming in to the Arduino through a voltage divider and be protected by a 5-volt zener. So we're going to be reading power directly, and then based on power we can do things like warnings, current sensor, approximations anyways, because we're not reading current, we're reading voltage. We'll be changing the display, etc., etc. Brake switch for the levers will be coming in. And then we're going to need a speaker. So we're going to drive a 12-volt, simple 12-volt piezo speaker from the Arduino. So we'll be doing a lot of interesting noises, status, a whole bunch of stuff. So, and if we have room left over, we're going to replace the front headlight, which sucks, with a proper one, hopefully driven from power, and same thing with a tail light. And that's the design. So let's start building it. All right, here we have the final build of the bike. So as you can see here, this is the controller that I built. So the controller hooks up to the existing wiring of the bike, including the torque sensor. Also, I wired in a throttle for the bike as well, so it can do either torque sensor or it can do throttle. I also interfaced with the display here, so it can flash the battery value on the display. Also put in a beeper as well, so you can hear sounds. I also went ahead and added a 24-volt LED light, substituting the original. And also I put a 24-volt strobe tail light inside the existing housing as well. So everything took about 4 months to get here. It was a very long and painful process. What I thought would be a very simple and straightforward project actually turned out to be a quite complex and involved piece of engineering. So I have a new respect for at least brushed motor controllers. There's a lot involved in it. So inside here there's a little Arduino, and of course, I mean, I've hot glued it all together now, but there's 2 MOSFETs driving it, and there's 2 regulators, and I mean, it just goes on and on, all that has happened to this. Mainly I've learned that, you know, making gate drivers for MOSFETs, very challenging. Avoiding transients, not just feedback from the inductor, but also ringing on the driver circuit, which cause feedback, which looks like transients, voltage spikes, dealing with voltage spikes, blow-ups. I had about 10 blow-ups on this board, and you know, it's so painful to work with a rat's nest of wiring and trying to keep it neat and tucked away. But I did it. It was actually fine and working. I got the torque sensor working. So every time you'd pedal, it would feed into the Arduino. Arduino would apply a PWM value to the wheel, and everything was fine. And unfortunately, I can't prove it because last week I had my last blow up, and unfortunately I hooked up positive and negative backwards, and I blew up my board, but I also blew up the internal torque sensor to the bike. So sadly, that means that the bike torque sensor is kaput, which means this is basically a useless bike. But it does have a throttle on it, so I'll probably just fix the battery up and sell it as a throttle-only bike. Sad, but I really got to like this bike. Anyways, so I'll fire it up and show you how it works. So I just hooked up the battery temporarily in the basket there, but this will give you an idea. So that's the start procedure I made. Basically, it just iterates through all the lights. So now it shows 100%. The tail light does a strobe pattern, which is controlled by the Arduino. There is a light in the front, so, and also horn as well. So this is the throttle. Essentially, you just pull the throttle and that's it. So also the gears work on this thing as well. So you can actually bang through the gears. So starting from 0, I'll switch to the gears. That's second gear, that's third gear, that's fourth gear. So it actually does pretty good. It goes pretty fast. For a throttle-only bike, it's actually quite nice. So that's it. So yeah, I'll finish it up, finish up the battery. I'll replace the bike seat, clean it up a little bit, button it all up, and this thing will be good to go. All right, so I'm going to begin the last part of this build, which is putting together a battery pack. So I'll be using lithium ion. Got a whole bunch of these Yardworks batteries at an auction. So I'm going to be just using these ones here. So I'm going to open all these up, take them apart, and harvest all the battery packs. So these are all these cool. This is all brand new, old stock battery packs. And I took apart one already and took a look at them. These are 2 amp-hour batteries with really low internal resistance. So these should make some great battery packs. So for the sizing, I'm going to probably use 7 series, 6 parallel, giving us 42 batteries, and so that will fit inside here with some room. So this is 10, so I'm going to go an extra row here, right? To give us 42. This is 4 by 10, 40. So one more row here, and it should fit nicely here with the BMS on the top or on the side, probably the top, and that will give us a good battery pack. So let's get started on that. Take these apart and put them on the load tester and make sure all the batteries are good. And then I'm going to put them all in series temporarily, do a load test on them. If everything's good, then we're going to solder them up. Okay, so I finished building up this battery pack. Turns out that these cells are no name. They're good quality, but they're not a name brand. And I think that these shells are super thin, because I tried to weld one of these things, and even on the weakest weld setting, I blew right through the case. So I do not want to weld these things. So instead, I took these as is, and I just used some thick copper wire to just connect the banks. So as you can see here, this is a strand of 5. So I left the original welds in, the original plates in, and so this is 5. So this is 1, 2, 3, 4, 5, 6. 6 times 5, and the rest of them I cut up and I just welded them in by hand. So this is basically 7S, 6 deep. This would give us 12 amp hours, and I already put this on the bench test. This is super strong. All these things are balanced. They're all in spec. So the battery pack is good, but yeah, you can't weld these. So anyhow, I'm going to weld in some BMS leads, and I'm going to be using this simple 7S 20 amp, very super tiny BMS. Probably mount it there at the top, so that when this thing sits vertically, BMS is going to be at the top. So I'm going to go ahead and solder these wires in, wrap it up, and finish up this battery. Okay, so the battery's put together, charge it up last night. So it turns out that the old battery charger wasn't working. Created a voltage, but there was a very weak current. So that's probably what happened to this thing. So this is a new Chinese charger. So light is green, trap is clean. So this thing now has a full charge. And last night I took it out for a spin. So on this 12 amp battery pack, I did about 1 hour on the bike, full throttle. So I'm 200 pounds. So this bike is good to go. Did really well. So we're going to go for a final ride. Yep, 100%. So battery is in good shape. I'm going to take it out for a ride and see how she does. Okay, here we go.
Okay.
I'm going to turn the bike on.
Okay.
Alright, so first gear. Ready? I'm going to try to go second gear. First, second, third. Second, third, fourth. All right, did that go? How was that?
Oh, great.